Welcome to this lecture. Now, the final NC estimator, consider an estimator j theta as follows. J of theta is the expectation of log h theta of x, where this expectation is with respect to px, plus u times the expectation of log of 1 minus h of y. See, this y and x are dummy variables, right? As long as we are sampling from the right distribution, it is okay. Now, this is the NC estimator. The NC estimator is this, that we find out the difference between the expectations of these two terms, where, or rather the sum of these two expectations, where the first expectation is that of log of h theta of x, and the expectation is with respect to px. The second expectation is with respect to log of 1 minus h of y, where the expectation is with respect to Pn. What is h theta here? H theta is whatever we saw in the previous case. So, h theta is that neural network which is trying to solve the binary classification problem between Px and Pn. Okay, it is that network. Now, the theorem says as follows. I will just state the theorem without proof. Take this proof as an exercise. I will give you the sketch of proof. You do it. Okay. The theorem is as follows. So, this j theta NCE attains a maximum at see, okay, so let me just define that as well once, just before we write the theorem, just to make it self sustained, where h theta, what did we define h theta to be here? H theta is 1 by this thing, right, and f theta of u is this, right. So, the same definition that we have, where h theta is given by 1 by 1 plus nu times e power minus f theta of u, and f theta of u was the difference between log of p theta of u minus log of Pn of u, correct. This was the definition. So, the theorem says that j theta NC attains a maximum at for those thetas for that theta for which f theta of u is equal to log px minus log Pn. This is the result, or we will call this as f theta of x, right. So, what we are saying is that this objective function would be maximized only if this f theta becomes equal to log of px minus this thing. So, which means that if this, only if this p theta of u, which is the implicit density estimate that this h theta is doing, is equal to px of x, this objective function does not attain maxima. Or in other words, this objective function will attain maxima only if p theta of u here will be equal to px. We are done, right. So, what we are saying is that you can solve this binary classification problem in the best possible way only if the implicit density estimate that your neural network h theta is imposing is equal to that of the data density. Now, how do you prove this? I will just tell you how to prove this. See, this j theta is an expectation with respect to px and pn, is not it? Okay. Now, this h theta has dependence on p theta of u. Write down these expand these expectations and you will have p theta there. We have to differentiate this entire expectation with respect to p theta, because we are seeking what theta would maximize this with respect to p theta, and you see what is the optimal value of p theta that would maximize this j theta. You have to differentiate this entire thing with respect to p theta, and what will be seen is that p theta which would maximize this is when p theta is equal to px. That is the result that will come out. Okay. So, this is noise contrastive estimation. All it is saying is that given data, construct another noise distribution and train a binary classifier that would classify between the points of data and points of the noise. Okay. If you have done this correctly, then the underlying neural network would have estimated the density from which data is coming exactly, is what it is saying. So, now what do we do with this neural network is the question that I will answer in a while. This is still not sampling, but this neural network can be now used as an embedding extractor. The intermediate layers representations of this neural network that we have trained for classification now can be used to extract embeddings for data, which can be then used for downstream tasks. Do you see what is happening here? Okay. So, this is NCE. So, NCE is not something that is used as it is in practice today. An improvised version of NCE which is called Info-NCE is what is used. We will talk about Info-NCE in a while, but is this idea clear? I will just stop here for a while and take questions if there are any. So, the moral of the story is as follows, right. So, now, and by the way, did you notice that nowhere in the entire construction that the normalization constant z appeared, right, because there is log of p theta and log of pn of u, right, the z which is the normalization constant gets cancelled away. So, you can use this with EBMs as well. Okay. In fact, the original paper that proposed this idea is titled this noise contrastive estimation of unnormalized statistical models, NCE for unnormalized statistical models. So, why is it called unnormalized statistical models is because they say that we are modeling p theta dash without the normalization constant. You can completely ignore the normalization constant in this particular treatment of density estimation, but you can't do that in the ML estimation. By the way, all the techniques that are based on this very idea of NCE are referred to as self-supervised learning. I mean nomenclature, right, if you want it. So, it is a sub category of unsupervised learning. It is called self-supervised learning because the supervision is now being created, right, during learning in I do not know, yeah. So, it is supervised by the self itself because there is how can you define the noise? The definition of noise comes from what is data. So, that is self supervision. So, you are solving a supervised learning problem, but the supervision is not through some external agency, but it is self generated, maybe that is why the name self supervised learning. All the techniques that work on noise contrastive estimation, they are called self supervised learning techniques. Okay. Right. Now, as I said, NC is not used as it is in today's practical world. What is used is its cousin by name Info-NCE. where the idea is simply that extend problem of NCE to a multi-class classification problem. Now, in NCE we solved a binary classification problem, right, where there is data, there is noise, try to classify between them. Info-NCE you solve it in the multi-class classification sense. So, what do we do that? What is the idea behind Info-NCE is as follows. Suppose xi is a data point define xi plus and xi minus as positive and negative counterparts Now, if you are given a data point xi, you define two other data points, okay, xi plus and xi minus, where xi plus is called the positive counterpart and xi minus is a negative counterpart. What is it? Xi minus is the samples of noise that we are talking about, okay, and xi plus is another data point from the exact same distribution. So, we had d and d dash, right, that is exactly what they are saying as xi and xi plus, okay. Now, then define a loss which is L Info-NCE as the categorical cross entropy, it is not the binary cross entropy anymore, the categorical cross entropy of log e power some g theta of xi plus divided by e power, okay, we can just say it this way. Okay, hold on, equal to 1 to k plus e power, just wanted to write both of them within one sum, can't be done, e power g theta of x I plus. See, what is this? This is the usual softmax that we are looking at. This is the estimating the probability of x I plus being the positive sample given a sample and everything else being negative. So, this is a k class classification problem. The classification is between xi being the positive counterpart and everything taken to be as the out of class samples. See, what does a k class classification task do, right? So, one of the k will be the actual class and rest of them are not the actual classes. Here the actual class is taken to be as x plus, okay, and everything else is taken to be as the negative class. In fact, in the way we have defined it, right, there are k number of negative samples here, you see. For a given data point, there are k number of negative samples which are not coming from that particular class and one of them is the positive class. You see this, okay, and this is the usual softmax where g theta is typically a neural network, right, it can be a deep neural network. So, what is happening here is that you take a neural network, give x as an input and there is g theta and you get this g theta of x, you can also call this as some z, which is the representation, okay, and then you have a softmax on top of it. Now, what are the labels for this? For a given point x, x plus is taken to be as the correct label, right, and multiple x minuses are taken to be as the wrong labels. Is this all right? Now, how do you train this neural network? You train this neural network using this L Info-NCE laws, okay, and post training you can use the output of this neural network as the embedding that you can use for downstream tasks. Now, what is happening here? If you look at it, we are trying to ensure that the alignment between xi and its positive counterparts is maximized, and the misalignment between xi and its negative counterparts is being minimized. That is exactly what is done in a softmax or a k class classification problem, is not it? You are trying to learn representation z in such a way that given a point it aligns with its positive counterpart and it does not align with its negative counterpart. That is it. I will take questions in a while. Okay. So, this is in NCE extended to k class classification problems, because there we were trying to separate between the data point and one negative sample. Here we are saying data point, its positive and n negative sample, k negative sample. So, this is a k class classification problem that is being solved, okay. And these methods, okay, there are multiple methods that build on top of this idea. See, one is what is called as SimCLR, okay. This was done for the image representation learning. This was a simple method for contrastive learning of image representation, that is what it stands for, SimCLR, okay. And these things are also called contrastive learning methodologies, because they stem from NCE, right, noise contrastive estimation. And what SimCLR showed, and this is a paper co-authored by Hinton, what this paper showed was, if you do this learning, NCE on ImageNet data set, this is completely unsupervised, right, we do not need any labels whatsoever here. Then use these representations and then train another classifier for the ImageNet classification task. So, ImageNet was the standard challenge that was there in that time, right, where there are thousands of categories, 1 million categories. It is a 1 million class classification problem with a 1k, right, or 1 millions of examples, and the number of classes was 1000. It was shown that the number of labels that you need to achieve the best accuracy for that task, it is reduced by 90% if you use z instead of x. So, what is the procedure? Given a task, you learn the representations using NCE or Info-NCE, and then use 10% of that data, use z as your representation and use 10% of the label data to train a classifier post hoc. That is a downstream task. If you do that, the accuracy that you would have gotten by using 100% of data can be achieved by using 10% of label data if you do this learning. As I said, in today's LLM training, okay, the first level of training that happens is via these kinds of techniques. This is called unsupervised pre-training or self-supervised pre-training, where you train to learn the representations without labels, and then you can do a supervised fine tuning, SFT it is referred to as. So, there is unsupervised pre-training and then supervised fine tuning. So, you do supervised fine tuning by using these kinds of representations. In fact, you can use the exact same network to do a supervised training as well once you have trained it in an unsupervised way. The only question that remains right now is, how do we get these negative samples? You see this. So, given some data set, how do we define these positive samples and negative samples is the question that remains yet. Different methods do it in different ways. So, I will just state a couple of ways to do it. Before that, if there are any questions on the philosophy or methodology of contrastive estimation, ask me. Yeah.
Positive and negative samples, are they kind of analogous to that skip-gram algorithm with negative sampling?
I mean, I have not talked about skip-gram, but, but since you are asking, yeah, it is analogous, yes, yeah. You had a question, yeah.
My question was that what exactly are the
we will show that. See, in the definition of contrastive estimation, Pn is any distribution that is not Px, right. Now, in the proof that I skipped, so what can be shown is the more the overlap between Px and Pn, the difficult is the convergence of that estimator to the true distribution, right. So, now there is a whole area of work around contrastive estimation where people have asked this question of what samples makes good negative samples. This is called hard negative mining. This is called the problem of negative mining. So, how do you mine the negative samples? Because the harder the negative samples are, the better the learning is. But if there is completely non-overlap in terms of supports, for instance, suppose you are looking at images, learn representations of images, you just take images of Gaussian noise as your negative samples, the learned representations will not be good at all, because the classification is easier that way, right. So, now you have to carefully mine the negative samples. So, people have tried a lot of methods to mine the negative samples in careful ways, and a lot of them are empirical. So, I will just state a few ways to do that, right. But yeah, but the idea is that you should get your negative samples correctly.
Sir, here the negative samples are the noise.
Correct, negative samples here are the noise, yeah, in the comparing with the NCE, yes. Okay. Yeah, so we will look at how to look at negative samples and positive samples. So, example of this thing in SimCLR is as follows. So, X is taken as an image. Yeah, the advantage of taking it as a multi-class, the question is what is the need to move from NCE to Info-NCE. What can be shown is the estimator, right, has a better bound is what can be shown. So, intuitively here is what is happening, right. So, you are getting negative samples for free, why do not you use it for better convergence? Because you can generate as many negative samples as you want, right. So, there is no reason why you should only have one negative sample per example, you can generate as many negative samples as possible. So, use that is the idea, okay. Now, yeah, so if xn is an image, x plus is taken to be as the augmented versions of x. So, which can be rotation, decoloring, etc., right, it can be anything. So, given an image, rotate the image, okay, so that becomes a positive sample, or you flip the axis, right, or you take out the color of the image, just use one of the channels and so on, these becomes positive examples. What is the idea? The idea is, suppose you want to learn the concept of dog, that was truly a slip of my mind, my tongue, okay. Suppose you want to learn what the idea of, yeah, wish there were a way to learn the idea of God by contrastive learning. There does not exist any such thing as that is known to the human beings, but you can still learn the idea of naturally occurring things by using these kinds of techniques. So, okay, anyway, so jokes apart, suppose you want to learn what the idea of an animal dog is, right. So, irrespective of whether the image of the dog is flipped by 30-degree angle, irrespective of the fact that you do not see a color, okay, and suppose you add some noise to that dog image, human brain will recognize that as a dog, that is the idea. Now, you learn the representation in such a way that as long as the image or the data point is being sampled from the true underlying distribution, it maps it to the same representation. Okay. Now, these are positive examples. What are negative examples? Any other image than X that has different semantics. Right, I will write the semantics within quotes. Now negative samples are the ones that is not a dog image. Now aren't we begging the question here? Now we started all this by saying that we do not have labels. Now we are saying to define what negative samples are. So we have to ensure that in the bag of our negative examples it should not be coming from the distribution that we are interested in, which is non dog images. Now do not we need labels for it? It turns out that if you make that is why, so you asked the question, right, why do we need multiple negative samples? Because of this. Now if you have one negative sample, now if you sample, suppose you are given a data set, now you sample one image and you take 10 augmentations of it that became positive. You want a negative sample, you sample randomly from the data set with replacement. Now what are the odds of having the semantics of this image different as this image is very low, no? I mean it can still come from the same dog category but a different dog. But we do not want the representations corresponding to two different dogs to be different. That is why if you increase the number of negative samples by a very large number, then the odds of all those coming from the same semantic class will be less, is the idea. That is why these techniques are shown to work extremely well if you make your batch sizes to be very, very large. So SimCLR for instance had a batch size of 4096 samples, which is huge for an image task. Typically the batch sizes would be of several tens of examples, right, 8, 10 and all that. Now we are talking of batch sizes of thousands of examples. So that is why then people started asking this question, how do we reduce the batch size in contrastive estimation, and how do we ensure that we sample good negative examples without having class labels. Now that is an active area of research, I will not go deeper into it, but you got the idea, right. At least in SimCLR, take a large amount of negative samples so that most of it will be from different semantic category, and for positive obtaining the positive samples, you take several data augmentations and call it positive. So I talked about multiple data augmentations here, right. You can have each of it as one positive example while you are training. That is how SimCLR is trained. Is that all right? Any questions here? Okay. Yeah, so I will stop this lecture with a mention on this particular technique which is called JEPA, referred to as joint embedding predictive architecture. So here the idea is you do contrastive learning by entirely eliminating the need for negative samples. Okay, so because negative samples create such an issue, right. So you try to eliminate the entire negative samples. How do you do that is the question. In JEPA what is done is as follows, right. Now given data, they mask several parts of data. So suppose you have an image, okay. Now mask this random region, mask this region, mask this region, call this as M1, M2, M3. Okay. Now ask the neural network to predict M1, M2, M3 given the rest of the pixels. So that is the task. The task that is being solved now, okay, is not classifying between the positive and negative samples, but it is that given the context, tell me what is missing, right. So this is also, I mean if you think about it from a learning objective perspective, it's the fill in the blanks, right. So if you are given an image, okay, and a jigsaw puzzle, you can only complete the entire puzzle only if you know what the entire semantics is. So the entire architecture, so there is still a neural network, right, there is a neural network, okay, that takes in the context is the remaining pixels, okay. It also takes the masks as inputs, and given the masks and the context, it has to predict the representations for the entire image. Now since we have the entire image as well, so we know the representations of this, we know the representations that has been predicted without those entire image. try to minimize the norm distance between these two representations, and that is the objective to train this. This also has a similarity between this idea called masked autoencoder that I mentioned in the previous class, right. If you are looking at sequential data, what you do is that you give a sequence as an input to a transformer. You do not give the entire sequence, but you give a masked sequence as an input, ask it to predict the entire token, which is predict the masked part of it. The loss is simply the cross entropy, any favorite loss that you have between the predicted sequence and the actual sequence. This is called masked autoencode. This is also called joint embedding predictive architecture. This has also been shown to be extremely strong excuse me, in learning representations, and this will reduce the requirement for labeled data in the downstream tasks. Okay, questions? Yeah.
For this Info-NCE, we are having like when we are taking X as an image, so that X is totally different. Like we are taking X as a dog, but what if we are taking variety of different dogs as an X?
That's okay. That's okay. So that you don't have that information at all. That is why the question that I am asking is, given an image and its semantic invariant transformations, I want them to be grouped into same category. Given a data point and its semantically invariant transformations, I want them to be grouped into the same category, right. And if the transformation, or if there is an image and semantically non-invariant image, okay, or meaning different semantic image, I want the representations to be farther. That is all. So every time you train, every time you can have a different dog image and you do the same thing. So network has no idea whatsoever about the underlying labels or semantics.
But my target is to differentiate between different types of dogs.
No, my target is to learn the representations for the given underlying data set. Remember, in entire unsupervised learning, the idea is to model the marginal density, that is it. I do not care what the semantics are. That is why I told you all this story, right. I mean, we do not care about labels. We are not partitioning the data space at all. We are trying to learn or model the entire marginal density by these techniques.
Like if my aim is say to differentiate between different weathers of a same scene, we have different
okay, fine. You can't do it with this.
We can't do.
You can extract the embeddings from this and use label data to train another neural network, that is it. So see, please note that the entire goal of unsupervised learning is learn the marginal density, okay, without semantics, and use it for whatever. See, in fact, what happens is as follows, right. I mean, in practice today, if you are given a problem, let us say in image domain, vision domain, you will not start training a classifier from scratch. So there are neural networks, large scale neural networks that have been trained in an unsupervised way on this. So for instance, vision transformers, we talked of vision transformers, remember, in JEPA uses vision transformers as neural networks, by the way. So there are vision transformers that are trained using SimCLR kind of techniques on ImageNet dataset. What you do is that you take your dataset with labels, pass all your images through the pre-trained neural network, okay, get the embeddings and train another MLP or a small neural network or a transformer on these embeddings for the problem that you want to solve. Because there are already such a rich embedding that has been extracted by training this for months and years and all these data sets, and most of these neural networks are available, the weights are available in public. So nowadays, I mean, it is very seldom that a neural network is trained from scratch for a given problem. You always take a pre-trained neural network and fine tune. Either you fine tune in the transfer learning way we did, but you do not take neural networks that are trained for classification tasks. You take pre-trained neural networks that have been trained on these kinds of contrastive learning tasks, because the representations that have been learned via contrastive learning or self-supervised learning are richer in the sense that they are learning the marginal, not the conditionals. Always take the neural networks that have been trained to learn the marginals. See, that is why generalists are better. So you can take a generalist and train them to be a specialist, but you can't take a specialist and make them generalists, right. It is difficult to do it that way. So, always better to be a generalist, very good generalist, and then take it and do a fine tuning on whatever specialization that you need. That is the idea. Now, this completes whatever I wanted to discuss on unsupervised learning. Okay. So, from next class I will talk about the sampling part, which is the generative part of it. A couple of classes on what the first class will be on the principles of what generative modeling is, and I will give you a few examples, and then 1 or 2 classes on reinforcement learning. So, that will complete the course. Okay. Thank you.